Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, so today I want to start a new topic, homological dimension of modules, and I am not sure how much homological algebra you know. Do you know what is homology? Do you know what is cohomology or nothing? Do you know what are the functors? What is the category? What is the functor? Okay, so I will not prove all the details, but I will give the complete definitions and results, and the best reference, as I said last time also, should look at the TFR pamphlet number 5, homological methods in commutative algebra, that is available on the website of the TFR. Okay, so before I do it, first I will say some words about why is it needed for us now. So remember, we have defined ring to be a local ring to be regular, and we want to define arbitrary commutative ring regular if localization at every prime ideal is regular local, right? One want to define this, but it is not clear from so far whatever theory we have learned about regular local rings, that if you have a regular local ring and if I have a prime ideal there and if I localize that prime ideal, then the local ring is regular or not, it is not clear, and for that we need homological tools. So we want to basically prove that when you have a regular local ring, then all localizations are also regular. This is what one wants to prove, and this does not follow from the theory so far we have. So only I want to remind you that we have a very particular case of this. We have proved it in one of the lemma. So I will recall you what we have proved. So if you have a polynomial ring in over a field in n variables, K field, and suppose we have a prime ideal P here, P is spec Kx1 to xn, and suppose height of P is m, then in one of the lemma what we have done is we have constructed m elements. So we have constructed in one of the lemma when we were preparing for Jacobian criterion. In one of the lemma, we have proved that there exist m elements, m polynomials in P such that when you localize at P, so in this ring Kx1 x2 xn, localize at P, we have this ideal P localized at P, this is an ideal here, this is a local ring with this is the unique maximal ideal, and this maximal ideal is generated by the images of this F1 to Fm. We have constructed F1 to Fm like this. So this precisely means that, so this is a local ring of dimension height, the dimension of this ring equal to height of P, and this M is also height of P. So that means we have proved that this maximal ideal of this local ring is generated by M elements. So that precisely means it is regular. But this is a very special case, a polynomial ring over a field. We have proved that. So, this has proved that corollary, that this ring is regular. Regular means, in general, let us record, if A is a commutative ring, we say that A is regular if for every prime ideal P, A local at P is a regular local ring. That means height dimension of this ring equal to minimal number of generators for its maximal ideal, and this is height P. That is the definition of regular, and we have proved that the polynomial ring over a field is regular, and there we have constructed these polynomials. So, the proof was not so trivial, it was the construction was dependent on some field extensions and so on. So, right now we are looking for a different kind of criterions. How do we decide a ring is regular or regular given local ring? How do you decide it is regular? Not so far what we have proved. So, that was one comment. Another comment I wanted to say that remember that recall we have proved also that if AM is regular local, then it is normal and A is a normal domain. Regular implies a domain that we have proved because we went to associated graded ring and then associated graded domain, therefore original is domain. Similarly, if associated graded is integrally closed, then the original is integrally closed. That is how the proof of this implication goes. And this is also true. This is true only when dimension of the ring is 1. So, this is the theorem, and I will try to just tell you how does one prove this side, but I will only sketch, and we should discuss details in our tutorial session about this proof. Okay. So, the main step in this proof is the following. So, we have one dimensional ring and we have given it in normal domain and we want to prove it is regular. That means we want to prove that the maximal ideal is principal. So, we need to prove M is principal, that we are proving this implication under the assumption dimension is 1. Okay. So, because dimension is 1, by our dimension theorem we know there is one element which form a system of parameters. So, that is, since the dimension A is 1, there exists A in M actually, such that this ideal generated by A, this has to be primary ideal, because its system of parameter means mod that it is finite length, that means mod that it is Artinian ring, that means M is the only maximal ideal there, the dimension is 1. So, that will mean that the radical of this ideal is only M, because there is no maximal ideal, there is no prime ideal other than 0 and M, and this A is non-zero element. So, it has to be, radical has to be M. And now you prove that there is a B, and from here now the next step is to prove that, show that M is principal. From here it is not too difficult to say, we will see it in the tutorial. So now what I want to recall a few things. What is the homological dimension of a module? So does everybody know? So I will assume that everybody know what a category is. C category. So category has objects and so called morphisms. And model example of the category, you should keep in mind that we are going to apply all these abstract things to the category of A modules. This. So I will only tell you in this case, and then you can formulate the statements in a general case. So here the objects are the modules, fix. A is our fixed commutative ring. A is a fixed commutative ring. And objects are the modules, A modules are the objects. And we are denoting by V, W, etc. And the morphisms are A linear maps. Or so called module homomorphisms from V to W, and the set of all module homomorphisms we are denoting by hom A V W. So this is another module, right? This is also a module because think of this. See, these are all maps from V to W and with a special property. So this is a subset of W power V. You know the set theory notation. Set theory notation is, if I have sets X and Y are sets, and if I have a map, the set of all maps from X to Y maps, that is also denoted by hom XY. If you want, you can write your sets, and this you can think this is a subset, this is precisely denoted by Y power X. This is just a notation, and this notation comes from let me not say more. So this is the notation. So with that notation, this hom VW is a subset of V power W power V, but W power V has an A module structure. Think of this as a copies of W, this is a product copies of W indexed by V. So this is same as product W, this product is over V, V in V if you want. So therefore this is a direct product of modules, W is a module, so direct product of modules, so therefore this is a module and this is actually a submodule. So where you prove is, if you have two module homomorphism, then the sum is A linear, the scalar multiplication is also A linear, and so on. So that means you are proving that this is a submodule of this. Okay. So these are the morphisms, and now what are we going? What we want to do? We want to study this category of A modules. To get information about the ring A, not just one module, a whole bunch of modules over the ring, and we want to study this properties of the modules and so on and so on. And from this we want to extract a definition, extract an information about A. That is the basic principle of studying these categorical things. Okay. Now, so first of all, what is a complex? Complex in this category A modules. And whatever we do it here, it is not so difficult to see that this will work in arbitrary category with reasonable properties. And for example, category of sets, category of groups, category of vector spaces, category of A modules, or category of topological spaces, category of whatever subjects you are studying, differentiable manifolds, and so on and so on, or category of algebraic varieties, and so many things. But we are concentrating on the A module category. So, the complex of A modules is it's a bunch of module homomorphisms, and they are connected to each other like this. So, you have a module V0, then V1, V2, and so on, and this side also. So, V minus 1, V minus 2, and so on, and there are maps here. This is D0, this is D1, and this is D minus 1. So, minus 1s are usually written up. It is easier to write positive number than the negative number. So, that is, this is D1, D2, and so on, right. So, this is a sequence of A modules and A module homomorphisms such that the composites are 0. That means D0 compose D1 is 0. This composition is 0. Any two composition is 0. So, this is usually abbreviated by V dot here and D dot here. Such a thing is called a complex, and this is without bothering too much about this, just write D compose D is 0. That means at any stage the composition is 0. Such a thing is called a complex of A modules. Now, we would have seen earlier also, when do you say sequence is okay, before I go on. So, for some reason, if this complex has only the positive non-negative part or only the negative non-positive part, that we will see that happens in good situation. So, then you call it a homology or cohomology. So, what is the homology? So, on this non-negative side, homology means, see, this is a complex. So, therefore, what do we know? For example, from here we know that image of D0 is contained in the kernel of D1. That is because the composite is 0. At each stage that happens. So, so this is a submodule, this is also submodule, and if I take the quotient module this by this. So, if I take kernel of D1 mod image of D0, this is some submodule, some residue class module, it is an A module. So, this is called a homology of this complex H for homology, and complex is this V dot, and also it is written at which stage. So, for example, here this is at this stage 1, right. So, you can write down at any stage, and the simple rule that when it is on the non-negative side, you write the suffixes on the suffixes. When it is on the negative side, non-positive side, you write suffixes upper one. Simple because instead of writing minus suffixes, it is better to write powers, upper notation. What is it called? Suffix and superscripts, right? So that's it. So that is the homology. Now that is the complex. So you have lot of, for this complex you have lot of homologies are attached to it at each stage, and similarly on the negative side also. So now I want to make a category out of the complexes. So that means what should we define now? Our objects are the complexes, and we want to define morphism between the complexes. And when I say morphisms, already the morphisms also had some rules among them, that composite of morphism is morphism. Also, we want to add morphisms and get another morphism. So to say that we want a category to satisfy some property like additive category. That means morphisms are not just sets, but they are additive abelian groups. So that is that, and and so on, right. So, that kind of property. So, in our case those things will be easier to check always. So, we will not bother much about the general categories. Okay. So, how do you define the morphism of complexes? Okay, we have two complexes now. So, let me call V and W. So, one is V dot and another is W dot, and this D is usually called a boundary. This is called what is it called? It's called a complex. The complex one. So, D dot, and here also T dot. Actually, the notation should be different. One way is to put V here and W here, okay, or just use the same letter, but be aware what you are writing. Okay, so here it is. Here it starts at Vn to Vn plus 1. This is Dn, and one before that is Vn minus 1, Dn minus 1. And remember, because I have written like that, obviously I have chosen the non-negative side. If I would have written on the other side, then this will be different, right. So, and Wn minus 1, Wn and Wn plus 1. So, this is also Dn minus 1, Dn, at least. Okay, once we write like this and so on, this side and this side also, right. This is have two complexes. Now, morphism of complexes is the family of morphism, A modulo morphisms like this. So, this is Fn, this is Fn plus 1, this is Fn minus 1. So, morphism between these two complexes is F, it is not single F, it is a family Fn, where Fn's are A modulo morphism from this. So, that these diagrams are commutative. So, morphism F of complexes F is Fn, which is, or F dot from V dot T dot V to W dot comma D dot W, such that this diagram is commutative. So, that means what? At each stage, if I take Dn V, then compose with Fn plus 1, that is same thing as this way, Fn Dn W. This is true for all n. Then you call it a morphism of complexes. Now, from this definition, it is obvious that if I have 3 complexes and morphism between them, then the composition of a morphism of complexes is again a morphism of complexes. That is, just put another bunch here, and then if this square is commutative, down square is commutative, then the total together is commutative. So, morphism composition makes sense. Also, identity from the same complex to same complex, there is obviously identity morphism. Identity morphism obviously commutes this. So, identity is also there. Therefore, it now it forms a category. Now, okay. So, what other things I need? Okay. All right. Now, the main thing what we will need all the time is so called diagram chasing. So, that will happen in the like this. So, now suppose I have a sequence like this. Now, I will use the x as a complex, x dot, this is one complex, y dot is another complex, and z dot is another complex. and I will not, let us suppress that D, understood that D is there, and when I say a morphism, that we understand from X to Y. Similarly, from here to here we understand, and if I want to put 0 here and 0 here, you are aware that when do you say a module, the short exact sequence of modules, that means X, Y, Z are modules, and this map is this is F dot and this is G dot, this map is injective. So, first think about modules, this is module, this is module, this is module, and this map is injective, that means exactness here. Here exactness means image of this equal to kernel of this, and here exact means kernel of this is image of this, that means G is surjective. So, G is surjective, F injective, and kernel F image F equal to kernel G, then you call a short exact sequence of modules. Now, when do you say such a sequence is exact for complex in general? That means at each, for each n, it is exact sequence of A modules. See, this will give you this, think of X as vertical like that, Y as vertical like that, these are vertical. So, they are maps like that. So, this is called exact, called short exact sequence of complexes if for every n 0 xn fn, this is fn, yn to zn to gn, this is exact. Now, we are come down to the modules, short exact sequence of A modules. So, that means, so that is Fn is injective, Gn is surjective, and image of Fn equal to kernel of Gn. Okay, so that is short exact sequence of complexes. Now, I will write a proposition and then we will prove it orally.